Welcome to another deep dive. Ready to dive into a paper that really makes you think about things a little differently.
Absolutely.
Today, we're in the world of particle physics with a paper that really makes you think about things we thought we knew.
Good.
Protons, electrons, those sorts of things.
Yeah.
It's by Nick Traff. Really fascinating stuff.
Yeah, we're talking about a question that seems deceptively simple on the surface. Why is a proton approximately 1,836 times heavier than an electron?
Hmm.
And maybe more importantly, why isn't it a nice, neat whole number?
Right.
Why 1836?
Right, that number.
Yeah, so that's what intrigued Triff. And this exploration led him to some pretty wild places. He starts by presenting this really intriguing equation early on. The mass of a proton is approximately equal to 694 times the square root of 7, multiplied by the mass of an electron. Now, you might be thinking, okay, but what does that actually tell us?
Yeah. Where are we going with this?
Right, exactly. What's so significant about this equation is that it hints at the possibility that the proton might not be as fundamental as we once believed.
Okay.
Instead of being this indivisible, building block of matter, it might actually be a structure composed of something else.
Hold on, you're saying that protons might have their own internal structure? That's a pretty wild concept.
It is. To understand Triff's line of thinking, think of it like this. Just as a hole in a semiconductor, which is essentially a missing electron, can act like a particle itself,
Okay.
Triff proposes that there might be holes in the very fabric of space. These holes could interact with electrons in a very specific way, potentially contributing to the structure of a proton.
That's a pretty radical idea. How does this all connect back to that square root of 7 in the equation? That part still feels like a mystery.
That's where it gets even more interesting. Turns out that the square root of 7 is also the similarity factor for a unique fractal pattern, the Gosper curve.
Fractals. Now we're talking geometry. Okay, tell me more.
Exactly. Now imagine a line that keeps folding outward, and with each fold, the new segment grows larger than the last one by a factor of, you guessed it, the square root of 7.
Oh,
That's the Gosper curve in a nutshell. This infinitely detailed pattern that keeps getting bigger, but in this very specific way.
okay, so we've got this Gosper curve growing by the square root of 7, and we've got the proton to electron mass ratio also involving the square root of 7. That can't be a coincidence, right?
You got it. Triff suggests that the proton's internal structure might actually mirror the Gosper curve pattern.
Interesting.
Imagine, electrons in those holes we talked about, arranged in a way that reflects this root 7 growth factor.
So it's like the Gosper curve acts as a blueprint for how these particles are organized within the proton. But how do you even begin to visualize something like that?
It's a complex idea, for sure. Triff takes this two-dimensional fractal concept and translates it into a three-dimensional model. He's suggesting that the proton's structure actually spans across 4 interconnected planes.
4 planes. Whoa, we're not talking about a simple structure here. This proton sounds like it's got levels to it.
In a way, yes. Each plane represents a different aspect of the proton's structure.
Right.
Triff delves into some really interesting geometry here, suggesting that electrons and holes could be arranged within these planes using a concept called close packing.
Close packing.
Yeah, think about how oranges are stacked in a pyramid at the grocery store that's close packing in action. Triff uses a similar concept to explain how those electrons and holes might be, intricately arranged within the proton, spanning across those 4 interconnected planes.
So he's mapped out this potential structure where the number of electrons, holes, even the empty spaces within these 4 planes, all add up in a way that reflects that initial equation. Proton mass equals 694 times the square root of 7 times electron mass.
That's the idea. Truss model connects each piece of the puzzle, even those seemingly random numbers, to reveal a potential bigger picture.
It's an incredibly detailed and fascinating proposal. I have to imagine that even Truving himself wouldn't claim to have definitively solved the mysteries of the proton, right?
Oh, you're absolutely right. Triff acknowledges that his paper raises more questions than it answers. It's a starting point for a whole new way of thinking about these fundamental particles.
This is definitely a lot to take in. We went from a simple mass ratio to complex fractal patterns and a proposed multi-layered structure of the proton.
Yeah.
What's really striking is how Trieff's model really pushes us to think beyond the traditional boundaries of particle physics.
Absolutely, and that's where things get really interesting. Remember those 4 interconnected planes that make up Trieff's proton model? Well, he doesn't just leave it there. He takes it a step further by proposing a connection between these planes and a fascinating mathematical concept, the four-color theorem.
Okay, now you've piqued my curiosity. For our listeners who might not be familiar, the four-color theorem basically states that you only need four colors to color any map so that no two bordering regions share the same color.
Right.
But how does that relate to the structure of a proton? That feels like a pretty big leap.
It's a mind-bending connection, isn't it? Triff suggests that the four planes in his model could be represented by those four colors, and then the arrangement of electrons and holes within those planes would dictate the coloring of each region.
So you're saying there might be this hidden link between the structure of matter, the nature of space itself, and this elegant mathematical theorem. That's a pretty profound implication.
Exactly. Triff's paper opens up these incredible avenues for exploration. It's like he's shining a new light on the universe, revealing patterns and relationships we might never have imagined before.
Definitely a lot to ponder. This deep dive has taken us from a simple equation to a whole new way of visualizing the proton.
It really has.
What I find most compelling is how this paper encourages us to rethink what we thought we knew about fundamental particles. It highlights how much we still don't know and the incredible potential for discovery that lies ahead. So to our listener, as you go about your day, maybe take a moment to consider that even the seemingly simple things around us, the very building blocks of matter, might hold mysteries more profound than we ever imagined. Who knows what other hidden patterns and connections are waiting to be uncovered?